This is the last segment on one-point compactification. Last time we have defined local compactness and given some examples. Any compact topological space is locally compact. A real line is locally compact. Then simply ordered set X equipped with ordered topology is locally compact if it has least upper bound properties. Then we have shown that Q and R omega, these are not locally compact. Nice spaces which are metrizable and compact Hausdorff, these are nice spaces. Now the question is, if X is not nice, can X be a subspace of a nice space? That is, does there exist a nice space such that X is homeomorphic to a subspace of that nice space? So more precisely, our question is following: under what conditions X is homeomorphic to a subspace of a compact and Hausdorff space? This is a theorem which answers the question. It says that a topological space X is locally compact and Hausdorff if and only if there exists a space Y such that X is subspace of Y, the complement of X in Y as single element, Y is compact and Hausdorff. Furthermore, if Y and Y prime are two spaces satisfying these conditions, then there exists a homeomorphism F from Y to Y prime, which is identity on the subspace X. So this is the uniqueness part. So last time we have proved this theorem rigorously. Now today we state and prove characterization theorem for local compactness. It says that let X be a Hausdorff space, then X is locally compact space if and only if for every point little x in the topological space X and open neighborhood Ux of X, there exists an open subset of X denoted by Vx containing X such that Vx closure is compact and Vx closure is contained in Ux. So we prove this theorem. So this is a characterization if and only if so we have two parts of the theorem. First we prove the easier part, that is the reverse direction. So here our assumption is following: for every point X in the topological space X and open neighborhood Ux of X, there exists open neighborhood Vx of X such that Vx closure is compact and Vx closure contained in Ux. So what to prove? We have to prove that X is locally compact. That is, we have to show that for any point little x in topological space X, there exists compact set Cx containing an open neighborhood of X. So consider Cx equal to Vx closure. As per our assumption, Vx closure is compact, and it is known that Vx is contained in Vx closure, because Vx closure is the smallest closed subset containing Vx. So Vx contained in Cx, and Vx is neighborhood of X. That's why X belongs to Vx and Vx contained in Cx. Therefore, X is locally compact. Now we prove the converse part. Here our assumption is following: X is locally compact. So we have to show that for given any point X and Ux open neighborhood of X, there exists an open neighborhood of X denoted by Vx, such that Vx closure is compact and Vx closure contained in Ux. So note that X is Hausdorff and locally compact, therefore it admits one point compactification. Consider Y the one point compactification of X, then Y is compact and Hausdorff. Now we define Cx equal to Y minus Ux. See, Ux is open in X, therefore Ux is open in Y, and this is open subset of Y of type 1. Okay, so Y minus Ux, this is complement of Ux in Y, therefore Cx is closed in Y, and Y is compact, therefore Cx is compact in Y. Now for the compact set Cx and the point X, we have disjoint open sets Vx and W containing X and Cx respectively. So first of all, Cx is compact, we have from second item, and X is not in Cx because X is in Ux. Ux is our open neighborhood containing X, so X is in Ux, therefore X is not in Y minus Ux, therefore X is not in Cx. Thus we have compact set Cx and a point X outside the compact set Cx. Therefore we have disjoint open subsets of Y. These are Vx and W, such that X belongs to Vx and Cx contained in W, and they are disjoint. Vx intersection with W equal to empty set. Now see, Vx closure is compact in X. So first of all, you see Vx closure is closed subset of Y. So Vx closure is compact in Y. That is for obvious. Now Vx intersection with W equal to empty. This implies Vx contained in Y minus W. Therefore Vx closure contained in Y minus W and Y minus W contained in X. Therefore Vx closure contained in X. Now let us put the things together. Vx closure is compact subset of Y and X is subspace of Y. Vx contained in X, therefore Vx actually compact subset of X. So now only to show that Vx closure is contained in Ux. Now see that Cx intersection with Vx closure equal to empty set. Now replace Cx by Y minus Ux, because Cx equal to Y minus Ux. So this implies Y minus Ux intersection with Vx closure equal to empty set. This implies Vx closure contained in Ux. Therefore we are done. Now here we have corollary of theorem 2. It says that let X be locally compact and Hausdorff of, and A be a subspace of X if A is closed subset of X, then A is locally compact. That is, our assumption is X locally compact Hausdorff of A is closed in X, to show that A is locally compact. Suppose X, little x be a point in A, then as A is subset of the space X, X is also a point in X, and X is locally compact. Therefore there exists compact subset Cx in the topological space X and open set Ux in X such that X belongs to Ux and Ux contained in Cx. Now we define Cx prime equal to A intersection with Cx and Ux prime equal to Ux intersection with A. Then Ux prime, this is open in A, and Cx prime, this is compact in A, satisfying X belongs to Ux prime and Ux prime contained in Cx prime, and this implies A is locally compact. Therefore we have corollary 1, and here we have second corollary. Basically here we apply theorem 2. So here the statement is exactly same, except we have replaced closed by open. It says that let X be locally compact and Hausdorff of, and A be a subspace of X. If A is open in X, then A is locally compact. So under this condition, so we have to prove A is locally compact. So our assumption is following: X locally compact house top and A subspace of X and A is open in X, then we show that A is locally compact. Let us consider some arbitrary point little x in A. Then you know this is given that A is open subset of X, therefore A is open subset containing X, therefore we consider Ux equal to A, and therefore Ux is open neighborhood of little x, and this is open in the topological space X. So by theorem 2, there exists some open subset Vx in X such that Vx closure is compact and Vx closure is contained in A. So Vx closure, this is compact, and this is compact in X, and Vx closure, this is contained in A. That implies this is also compact in A. Therefore we consider Cx equal to Vx closure, and this is compact in A, and this is straightforward to see that Vx, this is open neighborhood of X, that of course contains the point little x, and this is Vx contained in closure of Vx, this is exactly equal to Cx, and our point X was arbitrary, therefore for every point X we have compact set Cx and open neighborhood Vx of X such that X belongs to Vx and Vx contained in Cx. Therefore X is local, so therefore A is locally compact.